Let's talk about turbulent flow. So again, last lecture, the first part of this, we're talking about laminar flow. Laminar flow is a flow condition where laminar comes from this idea of layers, right? You have these layers, think of it like pieces of paper, that are just like sliding over each other. So there's not a lot of or no vertical movement of the fluid in that sort of transverse direction. It's all sort of moving in one direction. Now in turbulent flow, we have an entirely different situation happening. So first of all, like, how does turbulent flow arise, and like under which conditions does it arise? You might be wondering why I have a spring and damper up here. Well, turbulent flow is basically, well, it's related to the Reynolds number. So again, let's write out Reynolds number. The conceptual model is inertial forces over viscous forces. Right, and that is, in math, it is rho u infinity times x over mu. So if I know the relationship between inertial and viscous, then I can predict the kind of state of the flow. So, okay, so why, again, this spring? Let me just kind of sketch out this spring damper system and kind of show you what I'm going for here. So let's say we have some initial, I don't know, like this is like the zero position of this mass m. So let's start by like displacing this mass some distance delta. So you take that spring and you sort of stretch it, you displace it. If I have a situation where there's a huge amount of inertia associated with this mass, and the spring is a really, really weak spring, what's going to happen? Right, it's just going to go back and forth, and become not unstable in this case, but it's going to just oscillate wildly. Right? There's very little that's stopping this system from slowing itself down. Right? This, what I meant to say, is a really weak damper. Right? You have this spring, a really weak damper, and it's just sort of oscillating all over the place. So it might look something like oops, let's start with the point I marked, like this, right? Sort of going to do this. You can probably draw it better than I can. Okay, but now let's consider a situation where actually that damper is much more forceful, or it's a sort of a higher rated damper, let's say, relative to the mass that's being moved. So in that case, what's going to happen? Right? Are we going to see oscillation? Well, we take it, we displace this this weight up here, and we release it, and it does something like this. Right? It's a stable response. There's not an oscillation that's occurring. So turbulent flow is sort of like this, right? How is it like it? Well, in laminar flow is like the situation on the right. There's enough like shear force in the fluid that it damps out any sort of natural oscillation that happens. In turbulent flow, now you have enough momentum, enough the mass is moving with enough momentum, that little natural fluctuations that occur start to cause instabilities, and these instabilities cascade. And all of a sudden you get this really wild oscillating flow all over the place. So this is kind of the physical underpinnings of turbulent flow. I think you all kind of have seen this in some way, but let me just show you a video that I have. Hopefully it plays. So this video is an example of turbulent flow. So somebody put together this nice experiment where they have this plate and it sort of slides through this bath, and then you see this stationary camera, but the plate is moving. So it's like you're sort of flowing along with the fluid. So what they're trying to show you is they trip the flow up front. So there's not actually a transition to turbulence that happens right away. But now you can kind of visualize what's happening with the turbulent flow. Some things to notice here. So you can see that the Reynolds number is increasing. Right? This is flow over an external flat plate. So the key or the characteristic length here is x, the position x. So even though the system's not really changing, the fact that we're moving down the position of the plate leads to a higher Reynolds number. So this is now with, I think, a higher velocity. You can kind of see how it changes the characteristic a little bit. I think they do, yeah, so they do a side-by-side. So one thing that you see with the higher Reynolds number, so there's a lot more kind of violence to the movement. All right, I think that's enough. Get the idea, right? Okay, so that's kind of the idea behind turbulent flow. So let's talk a little bit in the last few minutes about the concepts that you need to understand turbulent flow. All right, so first of all, let's look at like this transition from laminar to turbulent. So first, when the fluid encounters this plate, you see the boundary layer start to grow. And so let's kind of draw the boundary layer as it's growing. At some point, it's continuing to grow, but there's a transition that occurs to turbulence. So the flow will kind of reach this tipping point where the inertial overcomes the viscous, and you start to see these instabilities form. So if we were to plot, like, let's pick 2 points here. So pick A and pick B over here. If we were to plot the velocity, let's call it the y velocity, as a function of time. So y velocity as a function of time. For A and B, what would we see? Well, for A, it's laminar. So we're just going to see something boring, right? We're going to see a flat line. There's basically no or little y velocity, and it's constant. If we look at point B, what are we going to see? Well, we're going to see something we're going to see something like this. Right? Sorry, let me correct one thing. This is not necessarily just y velocity. This is just overall velocity. So overall velocity. So for A, you see a constant velocity. It's not changing. For B, you see it's sort of oscillating around a value. There's like a mean value that's constant, but there's this randomness associated with the oscillation. So this is really like a characteristic of turbulent flow. You can kind of model it by assuming a mean value, but then there's this additional factor, this additional oscillation that goes with it that somehow affects the heat transfer. Okay, so it turns out, let's see, some summary for this. Transition to turbulence. So that occurs at Reynolds greater than or equal to the Reynolds critical, which is approximately 5 times 10 to the fifth. 5 times 10 to the fifth. It's 5e to the fifth. So for a flat plate, external flat plate, if you compute the Reynolds number and it's above 5e to the fifth, you can kind of safely assume it's turbulent. Anything below that, it's still laminar. And then the relationship between Reynolds crit and x crit is just, as you'd think, it's rho u infinity times x critical over mu. So if I wanted to solve for x critical, like if I wanted to solve for the position at which this transition would occur, I just plug in 5e to the fifth, my rho u infinity and mu, and then I can compute x critical. All right? Wow, time went fast today. Okay, so that's as far as we're going to go today. Next time we'll wrap up on turbulent flow and then move on to some other concepts. All right, thanks.